fellow researchers, and the attendees for this session of the conference. I would like to start with by thanking the session chair and the organizers of the conference for giving me the opportunity to present our work here today. And the paper that I'm going to present today has the ID of MCSI 2026-153, and title of our paper today is Hybrid EKF SMO Estimator for State of Charge Estimation of lithium-ion batteries. And this work was conducted in collaboration with my colleagues, Dr. P.V.V. Rama, Mr. I.N. Swamy, and Mr. B. Sampath Kumar. Let me begin by providing some background to our study. So we are currently working on battery management system and a few modules of battery management system. So battery management system is a very crucial part of electrical vehicles, grid energy storage, and portable electronic devices for safe and efficient operation of lithium-ion battery packs. So among many parameters, SOC, state of charge, is one essential function of BMS, where it is very important for charging, discharging control, as well as cell balancing, temperature thermal control, and remaining range prediction. So the problem with SOC is that we cannot measure it directly by any instrument. We have to estimate it. And while estimating SOC, measurement of parameters like voltage, current, temperature are very important. And along with that, we need to have a battery model, and we should have a handy estimation algorithm. So there have been many estimation algorithms. So one very important, very basic algorithm is Coulomb counting Coulomb counting method. The main problem with Coulomb counting method is that it actually counts the charge in and charge out during charge and discharging cycles. So if there is any error, measurement error, it integrates over time. So it becomes a integration error over time, and Coulomb counting will lose its way, and finally it will end up giving a wrong SOC value. So if sensor bias is added to it, it adds the complexity. Then the one among the very famous method is extended Kalman filter. Hereafter we'll be calling it as EKF. So it's a recursive estimation, and it integrates the models of the battery with the voltage feedback to minimize the drift. So this has been discussed in many of the standard literature, so I'm not going much detail into it. The very important thing that EKF requires is an accurate process as well as accurate measurement noise models. It basically works on a Gaussian noise model, with Gaussian distribution. And EKF is known for working well with linearity is there. If there is any non-linearity, EKF will deviate from its function. It may not be that accurate. So next, one more algorithm, one more method is a sliding mode observer. We'll be calling it as SMO from hereafter. It has a very good resistance to non-Gaussian disturbances. Unlike EKF, it can handle non-Gaussian disturbances. It has got very low computational complexity. The mathematical formulation is very simple. But the problem with this SMO is it is prone to chattering. Chattering is going here and there, left and right, while measuring while estimating SOC. So it won't usually give an good steady state accurate result like EKF, but during dynamic conditions, during harsh conditions, SMO will give you a good result, if not accurate, where EKF usually fails to give. So what is the motivation behind taking a hybrid model, such as I have explained EKF as well as SMO? In this research, we have we came up with an algorithm where algorithm will use both EKF and SMO estimators, but not at the same time. They will switch between these two, depending upon the SOC conditions. Now, so assumptions of EKF can be broken in practice due to the sensor faults, problems with the connections, temperature-dependent variations of the parameters, and EMI, electromagnetic interference. So the complementary strength of EKF and SMO motivate the development of this hybrid EKF SMO estimation process. As I told you, during harsh conditions, SMO will give us a good result. During normal conditions, or nominal conditions, EKF will give us a good result. So during nominal conditions, we'll try to use EKF, and during harsh conditions where there is huge noise and there is a initial estimate error, we will switch to SMO. How we do that? That is what we are going to discuss through the presentation today. And while we are transiting between EKF and SMO, we will go for a bumpless transition. So that also we will discuss. So instead of relying on a single estimation method, as I told you, we'll go for a hybrid approach where we'll use both EKF as well as SMO. SMO is used when there is noise and there are uncertainties or sensor faults. In those conditions, EKF performance will reduce, so we will switch to SMO in such conditions. So the main contribution of this paper is our hybrid EKF SMO estimator with a gated bumpless transfer. As I told you, we have used a bumpless transfer mechanism. Then an adaptive innovation threshold, the deviation threshold, based on the voltage sensor noise level. It selects either EKF or SMO at each sampling instant. So that sampling is also shown. While inactive estimator is synchronized with the active one to ensure smooth transition. This is where we come across this bumpless transfer. Then the proposed hybrid estimator is evaluated against EKF only and SMO only, and Coulomb counting methods using a second order RC equivalent circuit model for a lithium-ion cell of 2.6 ampere hour capacity. So second order RC equivalent model will have two RC circuits, one with a higher time constant, one with a lower time constant, to simulate the real-time conditions. The performance is assessed under a 1 hour dynamic drive cycle. That is, we have used a 3600 seconds drive cycle current profile across the test conditions. We have two test conditions, condition A and condition B. We'll discuss through this paper. Then the study shows that the hybrid EKF SMO estimator matches the EKF under normal operating conditions mostly, while providing significantly improved robustness under sensor fault conditions where noise is there, sensor fault is there, and other harsh conditions. The hybrid estimator outperformed the EKF. That we will see during the result discussion. Then, as I told you, we are going to use a second order RC equivalent circuit model. So here we are going to represent the electric dynamics of the cell to match with the real-time computational efficiency. We are going to use two different RC circuits. As you can see over here, this is one RC circuit calculation, and this is another RC circuit contribution. So the terminal voltage is calculated as the open circuit voltage pertaining to the state of charge condition at kth interval. We are trying to kth interval reduced, and the internal voltage drop is reduced, and voltage drop for RC circuit 1, RC circuit 2 are reduced. So that will be taken as the terminal voltage. So this is what the state space representation of the second order RC equivalent circuit model. I'm not going much detail into it. It's a very generalized equation. Then for the battery model, we have used the following parameters. We have, as I told you before, we have used 2.6 ampere hour capacity battery, and the internal resistance of the battery is 0.042 ohm. And the first RC branch has got resistance and capacitance of these values, and the second RC branch, where it will provide long time constant, has got these values. Then the current sensor noise is taken as 30 milliampere, and voltage sensor noise is taken as 4 millivolt. And as I told you, we are going to test it for a condition of 1 hour dynamic drive cycle. So extended Kalman filter formulation, this is also, as I told you, it's a very standard formulation. I'm not going much detail into it. So we have taken it from the previously implemented papers, and we have used that model. So EKF estimates the state vector by linearizing the nonlinear relationships at each sample instead of its Jacobian matrix. Then during each prediction step, the state vector error covariance are propagated using the state transition matrix A and process noise covariance Q. So the updated step is then used. The measurement innovation is computed from the difference between the measured and predicted terminal voltages, as shown over here. And Kalman filter is again, Kalman gain is again calculated, and then state estimation is done using this correction. Then the sliding mode observer, SMO formulation, is done in this way. SMO formulation is very close to the Coulomb counting prediction. So along with for k plus 1 instant SOC estimation, kth instant SOC is required. To that, the SOC is calculated using the charge that is going out of the battery or coming into the battery. So this is Coulomb counting, and a function is used here so as to implement the SMO. So this will give us the SOC at k plus 1 instant. So to reduce chattering, we are going to use sine function, and boundary layer saturation function is also employed. So where the boundary layer width, where this is the boundary layer width phi. So this will define the boundary layer. So as we have discussed before, SMO needs a very simple model. It won't require any statistic noise model such as EKF requires. Then the hybrid EKF and SMO architecture for gated bumpless transfer. So the proposed hybrid estimator executes EKF and SMO simultaneously at each sampling instant. So the EKF innovation magnitude mod y, either plus or minus, is compared with the adaptive threshold gamma rho v. So this is the threshold with which this mod y is always compared. If mod y exceeds the threshold gamma rho v, indicates it is outlier. That means it is significantly crossing the threshold. Then EKF update is skipped. Then we will use SMO. If this mod y is not exceeding the threshold, then EKF update is used for SOC estimation, and SMO will be skipped. So the selection between EKF and SMO depends upon this mod y, modulus of y. So whether it is exceeding the threshold or it is within the threshold, that decides which estimation technique has to be used. So this algorithm, the algorithm that what we have used in this research mainly focuses on that. And while transiting from EKF to SMO or SMO to EKF, there will be a bumpless transfer. So we will use the values of SMO as the initial value for EKF and values of EKF as the initial value for SMO, so that the transition is bumpless. There is no much change from one algorithm to another algorithm. Slowly it will recalculate and will give us the correct SOC. So the experimental setup, we have not used a physical test bench, battery test bench. We have done this on a simulation, and we have done, as I told you before, this is done on a synthetic 1 hour dynamic load current profile. I will also show you the load current profile which we have used. It is used for over 1 hour, 3600 seconds. So each second it is been SOC is estimated. So the sampling frequency will become 1 hertz. So this to simulate, to represent the urban driving cycle of electric vehicle, we have to simulate cruising, acceleration, and regenerative braking. The cycle is been tuned. The selected cycle has been selected in such a way that it simulates all these conditions, and the initial state of charge is considered to be 95%, and end state of charge is considered to be 27%. Over the range of 95 to 27, we have estimated over 1 hour, we have done the experiment simulation. Then the simulation scope and test conditions. There are two conditions under which we have tested this algorithm, hybrid algorithm. The one condition is nominal condition, where the noise is not non-Gaussian, it is a Gaussian noise, and sensor error is also not much. But in the second condition, where it is called elevated uncertainty, so here from here on we will call the first condition as condition A, and elevated uncertainty such as there is a too much of noise which is non-Gaussian, as well as the initial error, so that we call it as the elevated uncertainty. Apart from that, other conditions are normal, like we have used the 2.6 ampere hour battery, and it must be validated using a standard cell, EV cell. In the synthetic dynamic load current profile, as we have not taken it from a real-time load current profile, we call it as synthetic. So the load current profile as shown over here, as you can see here, this is the zero line, and most of the times the current is above the zero line, which is positive. When it is positive, that means the current is going out of the EV battery, that means it is discharging. And when current is negative, that means current is received by the EV battery. During normal conditions, it won't happen, but this happens because of the regenerative braking. Whenever regenerative braking is happening, it behaves as if it is charging, though the EV is running. So that is what the condition is. Then under normal dynamic load tracking, these are the two results that these are the few results that we have observed. The SOC estimation by different algorithms, Coulomb counting, EKF, SMO, and hybrid EKF, SMO. As we can see here, because of the initial error that it has got, Coulomb counting is a little away from the other algorithms. Coulomb counting is always inferior when compared to other algorithms. So only in condition B and condition A, we have used it. In condition B, anyhow, it will deviate much. In second graph also, we can clearly see the SOC estimation error against time when we have drawn. The error is very large because of the integration error of Coulomb counting method. Whereas in SOC estimation as well as SOC error, we can see all other algorithms are mostly going hand in hand with the reference SOC or true SOC. They are deviating a little here and there, but mostly they are following the reference SOC. And in the second graph, in the error graph, SOC error graph, we can clearly see that SMO is deviating a lot from the reference SOC error. So it is inferior when compared to EKF as well as hybrid EKF and SMO. Hybrid EKF and SMO, they are going mostly hand in hand. They are mostly similar under condition A. So let me show you. Yeah. These are the results, quantitative results. Uh, Whereas the EKF converges faster than SMO as well as hybrid. Whereas hybrid EKF and SMO converge much faster when compared to SMO. And the root mean square error also, if you see, for EKF it is 0.117, and for SMO it is 0.321, and for hybrid it is 0.208. So SMO error is much larger when compared to EKF as well as hybrid. Under normal conditions, nominal conditions, EKF actually outperforms hybrid EKF and SMO. But the beauty of hybrid EKF and SMO is not when we have condition A, that is nominal operating conditions, but when there are harsh operating conditions such as condition B, we will try to understand and appreciate the work of hybrid EKF and SMO. Under normal nominal conditions, EKF outperforms the other algorithms. So, and the switching behavior, I will show the switching behavior under nominal conditions. So these are the comparisons between Coulomb counting, EKF, SMO, and hybrid EKF and SMO. When and these bands that you see over here, they represent root mean square error and maximum absolute error and maximum error. So Coulomb counting is way behind all other algorithms where RMSE, MAE, and maximum errors are much higher when compared to other algorithms. Whereas EKF and hybrid, EKF is outperforming both the SMO and hybrid because EKF RMSE is much lesser when compared to other, as well as MA is also comparatively less than SMO and hybrid, whereas the maximum error is almost same in all the algorithms. Then, so this is for condition A. We can clearly see the results indicate that the EKF is very accurate under under the normal conditions and very high level of measurement noise. When the process of measurement and noise parameters are properly adjusted, EKF is showing us a very accurate result when compared to other algorithms. Its RMSE is as small as 0.214 when compared to other algorithms under condition A. Now, so it is very clear under nominal conditions, EKF is outperforming the other algorithms. Now let us see condition B, where yeah, this is the switching behavior that we have seen, the switching behavior between SMO and EKF. So the algorithm switches to EKF and SMO depending upon the error mod Y, as I have explained before. So under nominal conditions, these switchings are very, very less, but under condition B, there is a huge switching between SMO and EKF by the algorithm, depending upon the innovation value. So under condition B, while doing condition B, we have considered a non-Gaussian noise and initial switching error, initial sensor error. So the EKF, the RMSE is found to be around 0.78%. When you compare with SMO, SMO is much higher, which is 10%. And RMSE of the hybrid algorithm is 0.76%, which is just below the EKF. And if we compare MAE, the absolute error, it is 0.47 in EKF, whereas it is almost 10, 9.99 in SMO. And hybrid, it is 0.45, which is below EKF. So SMO is not doing a great job in case of harsh condition. SMO alone is not really giving us a good SOC estimation, but EKF is giving a better estimation, whereas hybrid is giving a best estimation. So the same things are represented over here, like I've explained before. And if we look at it from the percentage point of view, SMO, as I've explained you before, has got a great RMSE, which is not good, higher RMSE, which is not good. And it is leading to lower estimation accuracy when compared to EKF. So hybrid estimator has outperformed SMO by reducing the root mean square error from 10% to 0.76, which is about 92.4% of reduction, which is considerably very, very high. And MAE from 9.99 to 0.45, which is 95.5% reduction. So definitely from these statistics, we can clearly say that hybrid estimator is outperforming SMO. So SMO is in no comparison under condition B, harsh conditions. But when we compare hybrid with EKF, for the noise that we have considered, it has shown the RMSE reduction when we are using a hybrid estimator, the RMSE is reduced by 2.56 percentage. So it is considerable, but this can go a little higher or it can be a little more under much harsher conditions. So definitely hybrid estimator is going to reduce the RMSE when compared to EKF. So in our case, the case that we have studied, it reduced by 2.56% in case of RMSE, and in MAE, the absolute error, it has reduced by 4.26%, which is also a considerable percentage. So by comparing all these things, we can clearly say that hybrid estimator is outperforming both SMO. SMO, it is outperforming by a very large percentage, and EKF, it is outperforming by considerable percentages. So this is what the finding is. So the overall findings are that the hybrid estimator was found to be most useful for abnormal operating conditions, whereas EKF is found to be good for nominal operating conditions. But in real time, in reality, we cannot think in a way that the conditions will always be nominal. So the EV must be prepared. The EV algorithm must be prepared for the harsh conditions. So hybrid is definitely better when compared to EKF. So hybrid estimator has outperformed SMO by huge numbers that we have already seen. In both the test conditions, it outperformed the SMO. Then the future studies, what this can be further extended, the study can be further extended is by testing it on a physical battery. We can test it and we can get a better result and we can validate the simulation results. Further studies could also be conducted on an automotive grade embedded platform to compare the estimated against the EKF and SMO in terms of real-time performance of the computational load. And future research can also be performed to develop proposed framework for simultaneous estimation of SOC, SOH also, and internal resistance, which are other very important features that we need to look at it when we talk about electric vehicle. Then the low weight data driven correction module can also be added to enhance this estimation accuracy under nominal operating conditions, while retaining the robust and sensor disturbances that are going to happen in EV. So the conclusion of this paper is that this paper proposes a hybrid EKF SMO to estimate SOC in lithium-ion batteries for bumpless transfer, which are used in EV. And the proposed estimator was tested under a second order RC equivalent circuit model under synthetic 1 hour dynamic load drive cycle and compared to Coulomb counting, EKF alone and SMO alone. under all these under different operating conditions with varying levels of uncertainty. So the results demonstrate that EKF has the best estimation accuracy for nominal operating conditions, whereas under harsh conditions, the hybrid has got the better accuracy. So then the results are presented here to prove hybrid estimator EKF-SMO to be practical compromise between accuracy and robustness. So they also offer a very good foundation for future experimental validation and adaptive tuning of the parameters. And these are the references that we have taken from the standard papers. We have developed the concept. I thank each and everybody who have patiently listening to our presentation. On behalf of all the co-authors, I thank you one and all once again. Thank you very much.